Hello. Today we continue our exploration of chemical reactions by beginning to explore a concept known as stoichiometry. Stoichiometry is a big, scary sounding word that really just means we're looking at the amounts of things involved in reactions. We're going to see how we can perform calculations, for instance, that if we know how much of reactant A that we start with, how much of product C do we get out from that reaction? Or we start with this much of reactant A, how much of product B do I need in order to completely react with that? I like this slide, and I like to show this slide at the beginning of this lecture, because you can really see it, and we're going to talk about this in quite a bit of detail, but you can really see here that moles and being able to convert things to moles is central to this idea of stoichiometry. And really moles is central to any discussion that we have about amounts involved in a chemical reaction. And so those calculations that we learned how to do a few weeks ago are going to be very, very key for us here. Those calculations form the basis of these stoichiometric calculations that we're going to be doing. And so you might need to brush up on some of that. But we're absolutely going to be converting back and forth between moles and any other number of units a lot as we explore stoichiometry. And so a few different things that we're going to be looking at. We'll be looking at some mass relationships. We'll be looking at what we call limiting reactant problems, in which one reactant is in a limited supply. And we'll be looking at something called percent yield. Those are the things that we're going to be talking about today. In our next lecture, we'll go on to look at some chemical analysis and concentrations, and then look at some pH and other reactions in aqueous solutions. We probably won't talk much about spectrometry in these lectures. And so, like I said, in general, stoichiometry is the study of our mass relationships in chemical reactions. And what stoichiometry does for us is it provides some quantitative information about the amounts involved in a reaction, the amounts of products and reactants that we have. Stoichiometry at its heart is seated in the idea of the law of conservation of matter. Remember, we talked about that matter and mass must be conserved in a chemical reaction. Law of conservation of matter tells us that has to happen. And so our total mass of the products must be equal to the total mass of reactants that we had to begin with. And we'll talk about how we use that. But this also tells us why chemical reactions have to be balanced. They have to be balanced for that mass, so that our masses are equal of products and reactants. And so our numbers of atoms on the reactant side have to be equal to our numbers of atoms on the product side. So all the balancing that we looked at a couple lectures ago is very, very key to stoichiometry. Because those coefficients that we get when we balance, those what we call the stoichiometric coefficients, those are, remember the numbers in front of chemical formulas after we balance of a reaction. What they do for us is they give us a ratio of reactants and products. That ratio is going to give us a conversion factor, which will allow us to convert back and forth between the number of reactants and the number of products. Let's take a look at what I mean by that. And so here in this particular reaction, this is the combustion of methane. So CH4 plus 2O2 gives us CO2 and 2H2O. If we just think about this, and so far when we've been thinking about chemical reactions, we've been thinking about this in terms of molecules. You know, one molecule of CH4 reacts with 2 molecules of O2, produces 1 molecule of CO2 and 2 molecules of H2O. And so if we think about that, there's no reason that I couldn't bump those numbers up, right? Like, is there any reason that I can't say a dozen CH4s react with 2 dozen O2 molecules to produce 1 dozen CO2s and 2 dozen H2Os? Same thing, right? We're just scaling everything up a little bit. We're going to scale it up even more And the way that we're going to now think about reactions in stoichiometric terms is that 1 mole of CH4. So our stoichiometric coefficient here, the 1, that's going to stand for 1 mole. So 1 mole of CH4 reacts with 2 moles of O2 to produce 1 mole of CO2 and 2 moles of H2O. And so we can see from our balanced chemical equation here, if we want to know how many moles of water, how many moles of H2O are produced when 1.0 moles of CH4 react. And we can see just from our equation that for every 1 CH4 that we have, we produce 2 moles of H2O. And likewise, if we want to think in some more scaled up terms, if we have 2 moles of CH4, so if I happen to start with 2 moles of this, we can see again from our chemical equation, our balanced chemical equation, that for every 1 CH4 that I have, I produce 2 moles of water. So if I start with 2 moles of CH4, I'm going to produce 4 moles of H2O. And so our balanced equation, our coefficients here, provide us with a conversion factor to convert back and forth between moles of one thing in the reaction to moles of another thing. So here's another example. So here we have actually the combustion of ethane now, C2H6. So we want to know how many moles of water are produced if 3.0 moles of oxygen react. And so we're going to start with our 3.0 moles of oxygen, but then we're going to use our conversion factor of 7 moles of oxygen to 6 moles of water in order to perform our conversion. And we can see that here. So we start with our 3 moles of O2, and we can see that we have 6 moles of H2O to 7 moles of O2, and that's just coming from our stoichiometric ratios here. And then we just perform the calculation to get 2.6 moles of H2O. But we can see just from a dimensional analysis standpoint, we can see from analyzing our units that moles of O2 are going to cancel out. And so you're going to have to think about that. How do I set up my conversion factor? Just like any other dimensional analysis problem, how do I set up my conversion factor so that the moles of the thing that I need to cancel out are going to do so, and I'm left with moles of the thing that I'm looking for? From a significant figure standpoint, these are exact conversion factors. We consider these to be exact numbers, so they would technically have an infinite number of significant figures, which means that we pay attention to the significant figures of the information we were given. So we had 3.02 sig figs in our initial measurement, so our answer is going to have 2 sig figs. And so do not factor these conversion factors into your thinking with significant figures. And so let's look at another example. So iodine and fluorine react together to form iodine trifluoride. So the first thing we need to do is come up with our balanced chemical equation so that we can see what our coefficients are. We can see what our stoichiometric ratios are going to be. So we start just with our equation. Remember, iodine and fluorine are both diatomic molecules. So when they exist by themselves, they'll exist as I2 and F2. So I2 plus F2 react to form IF3. There's our iodine trifluoride. Next, we need to balance the equation. So we get I2 plus 3F2 give us 2 F3s. Now let's look at some of our stoichiometric ratios there. For every 1 I2, I'm going to need 3 F2s. For every 1 I2, I'm going to form 2 IF3s. And finally, for every 3 F2s that I have, I'm going to form 2 IF3. And so those are 3 different stoichiometric conversions that we can use depending on whatever it is that we're trying to calculate. We might have a calculation where we know the amount of I2 that we start with, and we need to know how much F2 we're going to need in order to react with that. And that would tell us that we're going to use our first ratio here. We might know how much I2 we have, and we want to know how much IF3 is formed. So, okay, we're going to use our second ratio. Or we might know how much F2, we want to know how much IF3, so we'd use our third. We might be going in the opposite direction too. And so don't get sort of stuck into this rut of thinking that you're going to have information about a reactant and you're going to find information about a product. Using these methods that we talk about, you can relate two of anything in the reaction. There's no reason that you couldn't be told how much IF3 is produced and backtrack that to how much I2 do you need. And so again, for that one, you would simply use our first ratio here because that relates our I2 to our F2. The difference is going to be how you actually set things up. Or sorry, in the example I just talked about, it would be your second, your IF3 to your I2. But again, it just depends on what things you're trying to compare. And so then what will change is how you set up your conversion factor. Remember, we can set up conversion factors however we need to, so the correct units the correct units cancel out, and we're left with whatever we're looking for. And so for our first one, there's no reason that we couldn't set it up as 1 mole of I2 to 3 moles of F2, or 3 moles of F2 to 1 mole of I2. Just depends on how we need to set things up. And so here's an example. How many moles of I2 do I need in order to form 4 moles of IF3? And so we would set it up just like this. 4 moles of IF3 is the given information. It's what we're told that we're starting with. And we want to compare that to I2. So we're going to use our 1:2 ratio, 1 I2 to 2 moles of IF3. And then we would see that we have to set up our conversion factor like this so that our moles of IF3 are going to cancel out and we're left with moles of I2. And so then we just carry through the calculation. 4 divided by 1, or 4 multiplied by 1 divided by 2. And we would find that we need 2 moles of I2. How many moles of F2 do I need to produce 12 moles of IF3? So again, our starting information is our IF3. And here we want to use our stoichiometric ratio of 3F2 to 2IF3. We're just going to need to think about how we need to set that up so that our IF3s cancel out and we're left with F2s. So we can see that we would need to set things up like this. 3 moles of F2 on top, 2 moles of IF3 on bottom, so that our moles of IF3 cancel and we're left with moles of F2. And then we carry out the calculation to get 18 moles of F2. And one last example of these, how many moles of I2 do I need to react with 1.5 moles of F2? So now we're comparing our 2 reactants together. So we can see that we're going to need our 1:3 ratio here. Again, our question is how we set that up. We're going to have to set it up like this. 1 mole of I2 on top, 3 moles of F2 on bottom, so that our moles of F2 cancel out. And I'm left with moles of I2. And so I get 0.5 moles of I2. You'll notice when I perform these calculations, and you'll see some other examples in a bit, that now it's going to become very important for you to be very anal about writing in moles of whatever it is that we're actually looking for. So moles of F2, moles of I2 here, moles of F2 here. Take those few extra seconds to really write out your units very carefully. We're going to have some, and we'll see some examples in a few minutes, we're going to have some of these stoichiometric calculations that are very, very long and multiple steps. And so the more that you're in the habit of really writing out your units, the easier it will be for you to keep track of what's going on. Okay. Sorry, I'm not sure why I can't advance my slides. For some reason I have an annotate. Ooh, let me get rid of this, that might be it. There we go, okay. Technology. So let's talk about how we go from one to the other. Let's say that I know how many grams of reactant A that I start with in some general calculation. I know how many grams of reactant A that I start with. And I want to know how many grams of product B are going to be produced. we cannot directly go from one to the other. There's no ratio, there's no calculation we can do that allows us to go from grams of one thing to grams of another thing in one simple step. What we have to do is go through moles as an intermediate step in there. We would first convert to moles of reactant A. And we just use our molar mass for that to go in between grams and moles. Now that we're at moles of reactant A, now we can use our stoichiometric coefficients, just like we were just doing, to convert to moles of product B. From there, we can use the molar mass of B to now convert to grams of B. This is going to be a very, very typical progression that will take in a lot of these different calculations. Note that moles are central to this, and being able to convert back and forth between grams and moles, and we'll look at some other examples of atoms to moles and volume to moles using molarity. But the bottom line is that we need to somehow convert to moles, and then we can compare our two different ratios. So one of the things that we're going to start with are just some simple mass calculations, where, again, we're going to go through moles first and then compare the two different compounds using our molar ratios, our stoichiometric ratios. And then we can go back to mass of our second compound by using its molar mass. It'd be a very, very typical progression. So we'd use our molar mass first to go from mass of our first compound. We use molar mass to get to moles of that compound. We can then use our molar ratios to get to moles of the second compound. And then our molar mass of the second compound to get to mass of that. And again, though, this all hinges on having our balanced chemical equation so that we're able to use these molar ratios to convert from one to the other. Now, one of the common things one of the common hang-ups that students run into in these problems is, I don't even know where to start. I've got all this information, Professor Staples, and I don't even know where to begin. What do I do? I will give credit to Professor Benedict on this one because I heard her use this expression and I loved it. When in doubt, mole it out. If you're sitting there and you don't even know where to start by converting to moles. Convert something that you have over to moles, and then think about what you might be able to do from there as far as using some molar ratios. But that will very often be your first step in a lot of these problems, is figuring out how to convert your given quantities, your given amounts, over to moles, and then you can go from there. And so let's look at an example. So again, we come back to our combustion of methane that we looked at. And we want to know, if we start with 8.32 grams of methane, how much O2 is actually going to be used? Likewise, how much CO2 and H2O are going to form if we're starting with 8.32 grams of methane? And so let's look at the steps involved. The first thing we want to do is use molar mass to convert the moles of the given amount that we had, or use molar to convert from grams of the given amount over to moles of the given amount. And so we're going to use our 8.32 grams, then divide by our molar mass in order to get to moles. Now again, you can see here where I'm being very anal about keeping all of my units in there. That really helps me keep track of where I'm at and what this 0.52 is. I need to know that this 0.52 is moles of CH4. After that, I'm going to use my molar ratio to convert to moles of the thing that I'm looking for. So I've got my 0.52 moles of CH4. I want to know how much O2 eventually, that's what we're trying to go for, is how much O2 do I need. So I'm going to use my molar ratio of 2 moles of O2 to 1 mole of CH4 to then see that I'm going to need 1.04 moles of O2. And then my last step, I'm going to use my molar mass to convert to moles of that thing that I'm actually looking for. So there's my molar mass of O2. So I'll take my 1.04 moles of O2 and multiply that by my molar mass. Now I want to show you here too that there's no reason that you can't do all of this in one big dimensional analysis setup. And so let's take a look at what that might look like. And that's the way, honestly, that I do these is by having just one big setup. And so we know that we are starting with 8.32 grams of CH4. And so our first step converting to moles of CH4. Then we're going to use our molar ratio, 2 moles of O2 to 1 mole of CH4. And then finally our molar mass of O2, 32.0 grams of O2 for 1 mole of O2. And we look and see what happened with all of our units. Grams of CH4 cancels out. Moles of CH4 cancels out. Moles of O2 cancels out. I'm left with units of grams of O2. And then I would just put all of this into my calculator. I would get 8.32 times 1 times 2 times 32.0, all divided by 16.04 times 1 times 1. Sometimes I just include the ones in there when I'm writing it out like this, just to keep track of things. But then you would multiply that all through and divide, and we get our 33.3 grams of O2. So you can do it all in one big, long dimensional analysis setup. And some of the examples that I'll show you later, we'll see that too. I don't know if you've seen me write things out like this, but sometimes I write my dimensional analysis in what I call a train track setup, and I'll just show you what that looks like too, because I'll do some other examples of this later on. I just don't want you to be thrown off by it. Sometimes I will set things up like this, sort of in these different boxes. It's the same exact thing. I'm just using boxes to separate all my conversion factors. So again, you can see it's the same exact setup. Everything cancels out that I need. I just sometimes write my dimensional analysis in boxes like that. Just helps keep things a little bit tidy, I think, and you're able to really see each individual conversion factor. It's the same thing. I just wanted to show you that different type of setup. And so that would be how to calculate the number of grams of O2 if we know the grams of CH4 that we're starting with. And so unfortunately, you can't really consult with your neighbor, or you can, maybe hop on Piazza, or if you're in some study groups, which I hope maybe some of you are doing that. But now try to do the same calculations and just find out how much CH2 and H2O will form. You're going to run through the same exact process, only you're going to use your molar ratios of CH4 to CO2 and CH4 to H2O, and then you will obviously use your molar masses of CH2 and H2O. And so go ahead and pause the video now and try to do these calculations, and then come back when you have the answers and we'll check it. So hopefully you came up with 22.9 grams of CO2 and 18.7 grams of H2O. If you didn't, go back and look at what you might have done wrong and see if you can figure it out and come up with these answers. So now let's look at another example. Same exact type of thing. We just have a different equation here. And so we have a reaction of aqueous calcium nitrate with aqueous sodium phosphate. We've got a precipitation reaction that is going to precipitate out some calcium phosphate. And we also have some aqueous sodium nitrate. And so we want to know if we dissolve 3.87 grams of calcium nitrate in water and react that with an excess amount of sodium phosphate, how much of the calcium phosphate is going to form. And we're given our molar mass information. And so you would perform this in the exact same way that we just did. We're first going to use our grams of the calcium nitrate that we're given, use the molar mass of that to convert over to moles. use our molar ratio to convert to moles of calcium phosphate, and then use our molar mass of calcium phosphate to convert that over to grams. And so again, I would go ahead and pause the video and see if you can perform this calculation. And then when you come back, I will work the calculation out for you, and we'll see if you came up with the same thing. So go ahead and pause the video now and try to run this calculation. Okay, you're back. Let's see what you came up with. Or let's see if what you came up with looks similar to what I have. So we're starting with our 3.87 grams of our calcium nitrate. We need to first convert that to moles of calcium nitrate. Again, note how careful I am to include all of my units all the time. Moles of calcium nitrate, grams of calcium nitrate. We're then going to use our molar ratio between calcium phosphate and calcium nitrate. And then finally, our molar mass of calcium phosphate. And we can see that all of our units cancel out the way we need them to. Grams of calcium nitrate disappears. Moles of calcium nitrate cancels. Moles of calcium phosphate cancels. We're left with grams of calcium phosphate, and then we perform the math. We'll have 3.87 divided by 164.09 divided by 3 times 310.18, and we get an answer of 2.44 grams of calcium phosphate. So hopefully you came up with the same thing. And so far, what we've been looking at is a sort of a straight gram to gram conversion, if you will. We've been doing a few examples of grams of a particular thing in the reaction compared to grams of another thing. But there's no reason you can't compare amounts in any way. And so there's no reason that you couldn't maybe start from a volume of a particular solution and use the molarity of that solution to get to moles, and then use your molar ratio. Use your molar ratio to then get to moles of the other thing in the equation. Oh my Lord, my mouse is so touchy. Okay. Get to moles of the other thing in your equation, then maybe use Avogadro's number to get to the number of particles. You know, you could take this pathway. You could maybe start with the volume of a particular metal, use the density of that metal to get to mass, then use the molar mass to get to moles, use your ratio to then get to moles, and then maybe use a molarity to get to volume. So you could take any of these pathways to compare any sort of amount of one thing in the reaction to any sort of amount of another thing in the reaction. But again, you'll notice what all of these pathways have in common is that we're going to use moles as the central part of that pathway. We have to first take whatever we're given for information for a given amount and convert that to moles, then our stoichiometric ratio to convert that to moles of the other thing we're looking for. And then from there, we can go to any other different type of amount using whatever information we're given. So let's look at a couple examples of that. And so here we have a reaction of solid aluminum with aqueous copper 2 nitrate, forms some aqueous aluminum nitrate, and copper metal precipitates out. And so in our first example, we're beginning with 575 milliliters of 0.250 molar copper nitrate and an excess amount of aluminum. And we want to know how many grams of copper are going to form. And so we can see that we're starting with a volume and a molarity So we're going to use this pathway to get to moles of the given information, and then our stoichiometric ratio. And then in this case, we're getting to grams. So we will just use our molar mass to get to grams. So let's take a look at that. Keep that up over here. Okay, and so we are starting with 575 milliliters of our copper nitrate. We can see the first thing that we're going to have to do is convert that over to liters, because molarity is in units of liters. So 1,000 milliliters to 1 liter. We know our molarity, so that's how we're going to convert over to moles, is 0.250 moles of copper nitrate per 1 liter. So now we're at moles of our copper nitrate. Now we have to use our balanced chemical equation to convert over to moles of copper. And so we're going to have 3 moles of Cu to 3 moles of copper nitrate. Now we can see in that step that, yes, 3 over 3 is just going to be 1. Mathematically, we wouldn't need that step in there. You still want to write that in, because that's our step of converting from moles of one thing to moles of another. So we need to show how we are actually doing that. And so I would definitely make sure to include that step, because again, that's how we're bridging between one thing in the reaction and another. Then our final step of those, to use our molar mass of copper, 63.546 grams of copper to 1 mole of copper. And again, we can see how our units are going to cancel out. Milliliters cancels, liters cancel, moles of copper nitrate cancel, moles of copper cancel. We're left with grams of copper. We do the math out from this, and we see that 9.12 grams of copper are actually going to precipitate. Sure, that looks like a U. Let's look at another example. And so here in this other example, we're starting with 2.63 grams of aluminum, an excess amount of copper nitrate, and we want to know how many atoms of copper are going to precipitate out from that. Okay, so now we're starting with 2.63 grams of aluminum. So again, our first step, the thing we need to do first, is convert to moles of this given thing that we're looking for. So we're going to use our molar mass of aluminum. 1 mole of aluminum is 26.98 grams of aluminum, just from the periodic table. And then our molar ratio to convert from moles of aluminum to moles of copper. So we have 3 moles of copper to every 1 mole of aluminum. So now we're at moles of copper. So now we're looking for atoms of copper. So now we're just going to use Avogadro's number. 6.02 times 10 to the 23rd. Atoms of copper to every 1 mole of copper. We can see that grams of aluminum cancels, moles of aluminum cancel, moles of copper cancel. We're left with atoms of copper. Plug it into our calculator, 1.76 times 10 to the 23rd atoms of copper. Let's finally look at that on our last example. So this example, we're told the volume of aluminum that we start with. We're not told the mass, we're told our volume. And then we want to get to the same information, how many atoms of copper are going to precipitate. And so now we have to just think about how we're going to get to moles from our volume. We can see that we're given density, and we know that if we can get to mass, then we can just use our molar mass. And so we can use our density to go from volume to the mass. So we're starting with 3.45 cms cubed of aluminum. And so we're going to use that density, 2.7 grams of aluminum to every 1 cm cubed of aluminum. And then finally, sorry, I'm just looking at my setup down here and I did something wrong when I wrote it out. But then next, we want to use our molar mass of aluminum, right? Because we need to go to the actual moles of aluminum. So 1 mole of aluminum to 26.98 grams of aluminum. Now we can use our molar ratio. 3 moles of copper to 1 mole of aluminum. And then finally Avogadro's number, since we're looking for the number of atoms of copper. And again, we see everything cancels out that we need to. So we would be left with atoms of copper. Plug this into the calculator. We're going to get 6.24 times 10 to the 23rd atoms of copper. So again, the point behind showing you all of those is that we can use any pathway within this whole sort of stoichiometric flow chart to get from the amount of one thing to the amount of another thing. And so it just depends on what information we have and what information ultimately that we're going to be looking for. So in the reactions that we've looked at so far, we've been making one basic assumption in that, so we've been told, for instance, that if we have a certain amount of reactant A, how much of product B do we make? That assumes that we have enough of the other reactant to react fully. That's not always going to be the case. In fact, very often it is not the case. So one of the things that we have to think about is what aspect or what reactant in our reaction is going to limit how much we're going to be able to make. And so think of it this way, and we'll look at some other analogies in a second, but I always love to use an analogy like this. Let's say you want to make your, even though you're not going to see me face to face, which is unfortunate, but you want to make your favorite chemistry professor some chocolate chip cookies. Actually, peanut butter chocolate chip cookies would be awesome. So you want to make your favorite chemistry professor some peanut butter chocolate chip cookies. And so you get rooting around through your cupboards to look at the things that you're going to need. And it turns out you've got tons and tons of flour, you've got tons of eggs, tons of peanut butter, tons of everything that you're going to need. But you've only got about half a bag of chocolate chips. That half a bag of chocolate chips would make, let's say, 30 cookies. Throw a number out there. And so even though you have enough flour, you have enough eggs, you have enough peanut butter, you have enough of everything else that you could theoretically make your favorite chemistry professor, I'm not saying it's me, but just in case it is, you would have enough of everything else to make them 100 cookies. The amount of chocolate chips you have limits how many cookies you could actually make me. That's the whole idea behind limiting reactants, is that there's going to be something in your reaction. There's one of the reactants that is in a short supply, and so it will limit how much product can actually be formed. And so the theoretical yield, and we'll talk about theoretical yield versus actual yield in a minute, but the theoretical yield, how much of our product we could theoretically make, is going to be limited by that limiting reactant. Let's look at another analogy that uses something that looks like an equation almost. So let's say that you have 32 nuts and 28 bolts. So we're just putting together some nuts and bolts. And in this particular set that we're talking about, each set just consists of one nut and one bolt. Maybe you're putting together some nice IKEA furniture that your wife decided to buy and you hate anyway. Don't get me started on IKEA. I don't know why I thought of it. But you're putting together some IKEA furniture, and so each set consists of one nut and one bolt. You've got 32 and 28. So we can think of that like an equation, right? One nut plus one bolt gives us one nut-bolt product. So how many sets can you make? How many nuts and bolts can you put together? We could only put together 28, because the number of bolts that we have limits how many sets we're going to be able to put together. let's say same thing. We have 32 nuts and 28 bolts, but this other particular set we're putting together requires 2 nuts on there for every 1 bolt. So now, how many nut bolt sets can we make? So now if we think of that like an equation, 2 nuts plus 1 bolt gives us 1 nut bolt product. And so how many of these products, how many NBs can we make now? Now we can only make 16, right? The number of nuts that we have is now going to limit how many of these nut bolt assemblies we can actually put together. And so you'll notice, and the thing that I really want you to take home from the examples that we just looked at, is that when you're figuring out what is going to limit your amount in a chemical reaction, you cannot simply look at how many or how much of your reactants that you have, because so much is going to be dictated by this chemical formula, right? In our last example, or in our first example, we only needed 1 and 1. And so our lesser amount was the thing that limited us. But in this example here, now our lesser amount is the bolts, but we have more than enough bolts because we need 2 nuts per every bolt in our set. And so it's actually this set of nuts. We can only make 16 sets total because that's how many nuts that we have. And so keep that in mind as we're going forward. And for our purposes, that's going to mean looking at the number of moles. You can't just look at the number of grams. You're going to need to convert over to moles first of all. And then you're going to need to look at these ratios. And we're going to talk about all that and look at how we do that. But we need to compare our ratios of how much we actually need and versus how much that we actually have. As a last example, so something sort of similar, if I have 27 wheels and 12 handlebars, how many tricycles can I make? I can only make 9, right? My wheels are going to limit. Even though I have a greater number of wheels, I need 3 wheels for every 1 tricycle. So I'm only going to be able to make 9 tricycles from these ingredients, if you will. And so let's take a look at what that's going to mean in a chemical reaction. And so here, we're starting with 50 grams of aluminum and 50 grams of O2 in a reaction of aluminum with oxygen. And so we want to know what the theoretical yield is for this equation. Our first step, so we have aluminum and oxygen coming together, our first step is that we have to come up with our balanced chemical formula for what this reaction is. And so that's what we have here. So we have our aluminum coming together with our O2. Remember, oxygen is a diatomic, so that is going to go in as O2. It's a synthesis reaction, just 2 elements coming together to form 1 compound. So then we come up with our chemical formula of aluminum and oxygen coming together. So we get Al2O3, and then we balance that reaction. So there's our first step done, our balanced chemical reaction between aluminum and oxygen. And so then our next step is to start looking at that 50 grams of each, see which one of those is actually going to limit us. Now again, like I was saying earlier, you can't simply look at the fact that we have 50 and 50 and say, oh, well, that's an equal amount, so neither one of them limits. First of all, we have to think in terms of moles as opposed to grams. Secondly, we have to consider our molar ratios after that, and that's what we're going to walk through right now. And so our first step, after we come up with a balanced chemical equation, is we want to convert our given amounts over to moles. And so we have our 50 grams of aluminum. We'll convert that over to moles of aluminum. So we're just going to use our molar mass. So we come up with 1.85 grams of, or 1.85 moles of aluminum. Secondly, we've got our grams of O2. We're going to convert that over to moles of O2 using the molar mass of O2. So we come up with 1.56 moles of O2. So all we've done here is we've taken the starting amount of grams of each, and we've converted that over to moles of each. What we want to do then is divide one by the other. It doesn't matter which you divide by which, as long as you stay consistent in the next step that we're going to talk about. Excuse me. So we'll divide one by the other. I happen to just divide by O2. So take our 1.85 moles of Al divided by 1.56 moles of O2. And the only reason we're doing that is to get us to 1 moles of one of our reactants. And so we do this to say that, okay, what we're starting with is a ratio. We have 1.19 moles of aluminum per every mole of O2. And so it is just to develop this ratio that we've got 1.19 ALs to every 1 O2. And so that's what we have. That's what we're given. We're given these amounts in our reaction. What we want to do now is compare that to the ratios that we actually need. So we look at our balanced chemical equation, and we see that we need 4 moles of Al to every 3 moles of O2. And then we divide that through. And so we can see that in our balanced chemical equation, we need 1.33 moles of aluminum to every mole of O2 that we start with. And so if we just think about what those are, or what those represent, what we have, the amount that we're actually given, if we're running this in the lab, we have 1.19 moles of aluminum per every 1 mole of oxygen. Our balanced chemical equation tells us that what we need is 1.33 moles of aluminum for every mole of oxygen. And so think about that for a second. We need 1.33 moles of aluminum to every mole of oxygen. Do we have that? We don't, do we? We have 1.19 moles of aluminum per every mole of oxygen. That means that aluminum is the thing which limits us in this reaction. Aluminum is what we have in the least molar amount for the ratios that we need. Aluminum is our chocolate chips. Well, those are what we have the least amount of that will limit how much aluminum oxide can actually be formed. And so then once you have that information, you simply then take the 1.85 moles of aluminum. So remember, this is the actual amount that we started with. This is just our relative ratio. Our actual amount of aluminum we started with was 1.85 moles. And we can then just carry the rest of the reaction through like we've seen. Take our 1.85 moles of aluminum, multiply that through by our molar ratio, 2 moles of aluminum oxide to every 4 moles of aluminum, and then by our molar mass of aluminum oxide, gets us to our grams of aluminum oxide. Sorry. And so that tells us how much aluminum oxide can actually be formed if we have 50.0 grams of aluminum and 50.0 grams of O2. Aluminum is our limiting reagent. That one's going to limit how much aluminum oxide can be made. O2 is our excess reagent. We're going to have some O2 left over. And so this reaction will be all said and done. We're going to have all of the aluminum will be used up. We'll have 94.3 grams of aluminum oxide, and we'll still have some oxygen left in there. We'll look at another calculation in a little bit to determine how much oxygen is actually left. There is another way to do this. You can either run through it like this, doing sort of this molar comparison of how much you have versus how much that we actually need. Another way to do this is to simply carry out the whole calculation in the exact way that we've seen several examples of at this point. Carry out the whole entire calculation. Sorry, it looks like my spacing's a little off on these. But you carry that whole thing through. Let me just pause the video for 1 second. I'll be right back with you. Okay, that was going to bug me if I didn't fix it. And so you can carry the whole reaction out the way that we've done before, but you would just do it twice. You would do it the first time with your starting amount being your 50 grams of aluminum, and then do it a second time with your starting amount of 50 grams of oxygen. And we can see that if we do that, so starting with our 50 grams of aluminum, we first convert that to moles of aluminum. We use our molar ratio to convert to moles of Al2O3. Use our molar mass to convert to grams of Al2O3. And we come up with our 94.3 grams of aluminum oxide. And then we run the reaction, or we run the calculation, starting with our 50 grams of oxygen, use our molar mass of O2. Oh, another mistake. I don't know why I didn't catch that. Hold on. All right, fixed, and I feel better now. Of course, I somehow, there we go. So we start with our 50 grams of aluminum, use our molar mass in order to convert that over to moles. Sorry, our 50 grams of oxygen, our molar mass to convert that to moles of oxygen. Then our molar ratio between aluminum oxide and oxygen. Sorry, 2 to 3. And then finally, again, our molar mass of aluminum oxide. And we can see that 50 grams of oxygen forms 106 grams of aluminum oxide. So if you do this, if you perform the calculation this way, whatever the lesser amount is, that starting material is your limiting reactant, and that's how much can actually form, right? So just think about that. If I have 50 grams of aluminum, I can form 94.3 grams of aluminum oxide. 50 grams of oxygen forms 106 grams of aluminum oxide. But I can't make 106 grams of aluminum oxide. The amount of aluminum that I have can only make 94.3. And so aluminum has to limit our reaction, and we're going to form 94.3 grams of aluminum oxide. Now, everything that we've been looking at so far, so like this 94.3, for instance, that we said that we can make of aluminum oxide, that's what we call a theoretical yield. So theoretically, based on having 50 grams of aluminum and 50 grams of oxygen, I can theoretically produce 94.3 grams of aluminum oxide. That's if everything goes absolutely perfectly. My reaction runs perfectly the way that it should. I recover all the aluminum oxide that I actually make. And that in itself can be quite a process. And so the bottom line is that if I were to actually run that reaction, there's no way that I would actually get 94.3 grams of pure aluminum oxide. I just wouldn't. It's again, even in recovering it, so if I run this reaction and then I get my solid maybe, and then I have to filter that, some of it probably is going to run through and then accidentally go down the drain, no matter how careful I am. I'm going to dry it out. I might get some impurities that pop up in there. Maybe the reaction didn't go to completion for some reason. You know, I started with my 50 grams, but only 45 grams of aluminum actually reacted. Maybe I didn't heat it up enough if the reaction needed heat. Any number of things. And so what we want to do is we want to compare that theoretical yield. We want to compare how much we said we could make. That's our maximum, right? That the yield that we calculate, that 94.3 is the most aluminum oxide that I would be able to create. But I'm never actually going to get that. So we're going to compare that theoretical yield to the actual yield. So if I really run this experiment, how much aluminum oxide do I really get in return? And we're going to use those numbers to come up with what we call our percent yield. Percent yield is the amount, or it's the actual yield, how much we actually are able to get, then just divided by our theoretical yield, and then we simply multiply that by 100 to convert it to a percent. And so let's look at an example. And so again, the amount that we expect is our theoretical yield. The actual yield should be less than the predicted. So our theoretical yield, remember, is our maximum. If the actual yield is, sorry, I'll hold off. We'll talk about that in a minute. But we might have impure reactants, and so that 50.0 grams of aluminum might have had some other junk mixed up in there. Maybe it wasn't all aluminum. So that could yield to, that could lead to actuals being less than theoreticals. Maybe there were some byproducts. So along with aluminum oxide, something else might have been produced in there. And so that led to a lower yield. An incomplete reaction. Not all of that 50 grams actually went through for some reason. And so we run our percent yield calculation. Could be a very common type of calculation that's performed, especially in synthetic chemistry, for people who are working on producing new compounds. This is a very common type of calculation that will be done. Those of you who go on to organic chemistry and organic chemistry lab 252, Chem 252, you'll be running this percent yield calculation a lot. What you do pretty much every week in there is make a new compound, and you're always going to need to compare how much you actually make to your theoretical. There are times that actually your percent yield might be 1%, and that might be actually pretty good because of the mechanisms involved of recovery and purification and everything else. But okay, so let's look at an example. And so from our calculations, we determined that 94.3 grams of aluminum oxide could be formed from our reaction between 50 grams of aluminum and 50 grams of oxygen. So that 94.3 grams, that's our theoretical yield, how much aluminum oxide could theoretically form. Let's say I run the reaction and I actually am able to collect 48.5 grams of aluminum oxide. That's my actual yield. So now to find my percent yield, I'm going to take my actual, my 48.5, divide that by my theoretical, my 94.3, then again, multiply that by 100 to convert that over to a percent. And so I would come up with a percent yield of 51.4%. Let's put all this together into one big, long practice problem. And so 10 grams of gold, 10.0 grams of gold, and 10.0 grams of chlorine are sealed up in a container and heated until the reaction is complete. And our product is gold 3 chloride. So we want to know what is our limiting reactant, what is our mass of gold chloride that is formed, and what is our mass of the excess reactant, how much of our excess reactant remains after the reaction is complete. I actually have all of this on another video. Hopefully you've been watching some of my supplemental videos that I have on the website. But I have all of this worked out in one of those videos, and so I would encourage you to watch that. And so there's the link for it right here. You actually want to start it at about 8 minutes in for this particular problem, but just to show you where that is as well. So again, if you just go to the website, we're in Unit 2 now. Unit 2 materials. We come to some of our videos. And it's in this one right here, Stoichiometry, Limiting Reactants. And so if you start this one at 8 minutes in, then we have that problem. And so I would encourage you to do that. I would play the video for you right here, but just the sound, it wouldn't be a good quality trying to run it the way that I'm making my lecture videos. But I definitely encourage you to try this problem, try a lot of it on your own if you can, and then go through and watch this video and see how I solve this. And so go ahead and pause the lecture video now, try to do that, or go back later and watch it. But then just here are a few other examples. Again, unfortunately, you're not at desks. You're not at desks with each other, but hopefully you're at home and able to, or you're somewhere that you're able to work some of these examples. And so here are several examples, and I'm just going to leave these up, and then I will show the answer. Again, I would definitely pause the video now and work this through. You have a certain amount of silicon dioxide and a certain amount of carbon. You need to know the theoretical yield of the silicon carbide. And so the first thing that you're going to have to do is figure out the limiting reactant. And then based on that, how much silicon carbide is formed. So pause the video now, try to work it out, and hopefully you're able to come up with the answers. The answers to this are that the silicon dioxide, our SiO2, is our limiting reagent here. And we will be able to form 3.34 times 10 to the third grams of our silicon carbide. Here's another one. So DDT, an insecticide banned in the United States, because it's very, very hazardous. We see how it can be prepared, so that's how we would actually make it. And so here we're told that we're starting with 451 grams of our chlorobenzene. We have 368 grams of chloral, and we run this reaction, and what we actually get are 507 grams of DDT. And so you want to find several things in this question. You want to find out what is our limiting reactant, either the chlorobenzene or the chloral. From there, you're going to need to calculate the theoretical yield based on that limiting reagent. And then once you have the theoretical yield, you can use the actual yield to calculate your percent yield of the reaction. So again, go ahead and pause the video now and then run through this and see if you can come up with the answer. Hopefully you found that chlorobenzene is what limits our reaction. The theoretical yield is 709 grams of DDT, leading to a percent yield of 71.5%. And then lastly, we want to know the percent yield of ammonia, NH3, if 50 grams each of nitrogen and hydrogen react to form 30 grams of ammonia. And so ultimately, we're just looking for the percent yield. So again, though, we need to know what limits our reaction. Based on that, how much ammonia, how much NH3 is produced. And then we're told that our actual yield is 30 grams. So based on that 30 grams and the theoretical yield, what is our percent yield? So pause the video now, work this out, and hopefully come up with answers of N2 is our limiting reagent. Our theoretical yield is 60.6 grams of ammonia, leading to a percent yield of 49.5%. So if you're struggling with these, definitely let me know. Actually, I will make a note to myself to work out my work for these samples, and I will post them either in video form or just a sheet showing my calculations. So I'll have those posted sometime later on. And so that's it for today. A lot of material covered. We've looked at a lot of our basics of stoichiometry. The big thing to remember, if you get stuck, is everything centers around the mole. Being able to convert your given amount to moles, using your molar ratios to then convert that to moles of whatever item it is, whatever compound it is that we're looking for. And then we can go from there for whatever information that we want as our final answer, grams or a volume, whatever it might be. We talked about limiting reagent, that something in our reactants, one of our reactants is always going to be limited, and how we deal with that. And then comparing that theoretical yield that we calculate with the actual yield that we get from the reaction. And so that is all for today's lecture. And next time we will talk about how we can use some of these stoichiometric principles in some various types of chemical analysis and some other factors involving stoichiometry. So that is it for today. I hope everyone has a great day. Thanks for watching.